So if you want to, you can even make a little note, not on test. This is going to be an introduction to the concepts. I'm not going to dive into the math. You may have noticed in this unit, every situation that we've looked at has had an acceleration of exactly what? 0 meters per second squared. Put your pencil down, look up.
No doubt you've heard that there are two theories of relativity, the special theory of relativity and the general theory of relativity. So naturally you want to know what's the difference between them. Well, here's how it goes. Einstein was obsessed with understanding how the world, how the universe would look to someone who's moving through the universe. You wouldn't think that that would be the key to understanding reality, but it turns out that it's a vital question to ask. Now, in the special theory of relativity, Einstein focused on observers that were moving with a very special kind of motion, constant velocity motion. That means motion at a fixed speed in a fixed direction. Now, even with that restriction to that special kind of motion, Einstein realized that you could extract some deep insights into the nature of reality. He was able to figure out that at constant velocity motion, an object would be squeezed, it would be compressed along the direction of that motion. And if you want a more realistic version of that, you can have a taxi cab moving down Fifth Avenue, going at very high speeds. That taxi cab would appear to be compressed along the direction in which it's moving. And in fact, if you were to jump in to that taxi cab, Einstein's insights tell us that the outside world would undergo some really wild-looking distortions because of the impact of constant velocity motion on space and on time. Deep insight. Now, that was 1905 when Einstein came up with these ideas. 10 more years of working and thinking and calculating allowed him to generalize this theory to motion that was not constant velocity motion, motion in which the observer could be speeding up or slowing down or going around a bend, what we call accelerated motion. And it's not obvious, but that move from constant velocity motion to accelerated motion, it turns out brings in an understanding of the force of gravity. So Einstein realized that by now including generalized motion that would include accelerated motion, he could get an understanding of the force of gravity in terms of warps and curves in the fabric of space and time. One of the most beautiful insights ever. So in a nutshell, that's the difference between the two theories. Special relativity focuses on motion at constant velocity. General relativity generalizes that to include motion that can be speeding up or slowing down, accelerated motion, and in so doing, it turns out, brings into the theory an understanding of the force of gravity.
That's the big difference between the two. Special relativity, Einstein didn't know how to work in gravity or changing your direction. General relativity was his aha moment. So special relativity only works when we have a constant speed. Pause for a second. So Einstein published his paper on special relativity in 1905, but already then he was starting to wonder, how can I include acceleration? How can I speed up, slow down, or change direction? And he thought about this intensely for years. And 2 years later, in 1907, he had what he called his happiest thought. This was his well, for lack of a better word, aha moment. This is where he suddenly saw how he could do it. He was sitting in his chair in the patent office in Bern where he was at work, and he was wondering what it would be like to drop a ball while you were in free fall. He imagined somebody falling off of a building. We'll make sure they don't hit the ground and die, just as a thought experiment. And he asked, while they were in the air, if they let go of a ball, what would they see? Well, to them, because the ball is in free fall, here's the ball, and they are in free fall, they would see the ball just staying level with them. For them, in their reference frame, it would appear as though the ball had no gravity. Now, someone watching them would see them both accelerating at negative 9.8 meters per second squared. But the person in free fall, when they let the ball go, and again, as always, we're ignoring air resistance. Let's pretend we're in a vacuum. They would see the ball moving down at 9.8 meters per second squared. Well, so are they. The ball would appear to them to be floating. And this was his hook. He's, I've got the same situation from two different reference frames. In one of them, we have acceleration, someone watching from on the street. In another one, in the person in here doesn't detect the acceleration. This was his aha. So Einstein realized that a person who accelerates downward along with the ball would not be able to detect the effects of gravity on it. An observer can transform away mathematically gravity, at least in the immediate neighborhood, by moving into this accelerated frame of reference, no matter what kind of object is dropped. He said gravity is, at least locally, equivalent to acceleration. And in fact, we've given this a name. This is called the principle of equivalency. If you hear someone talk about Einstein's principle of equivalency, he said acceleration, gravity, same thing mathematically in this specific situation. Put your pencils down, look up. You're seeing a lot of Brian Greene videos because he's one of the world experts on general and special relativity. He's also a good communicator. And he has fancy graphics.
In 1907, Albert Einstein was sitting in the patent office in Bern, Switzerland, when he had a thought that later in life he would describe as the happiest thought of his life. It was a thought that ultimately would lead him to the discovery of the general theory of relativity. So what was that thought? Well, he began to think about a person who might be falling from the roof of a building. And he realized, putting air resistance aside, that freely falling individual would not feel his or her own weight.
That's also true. When I jumped out of an airplane, when I jumped out of an airplane, I did feel weightless. I couldn't feel gravity. I know gravity is acting on me intellectually, but I couldn't feel it. Because what we think of as weight is actually the floor pushing up through our feet or the chair pushing up through our body. That's how we know gravity is acting on us. Remove that while you're in free fall, you feel weightless, even though you're not.
That individual would feel weightless, like they're floating in outer space. Let me show you what I mean. So let's take our protagonist over here, hanging from the roof of a building, holding on, as you see, to a little apple. So the individual goes into free fall motion, and I want you to look at how the apple appears from his perspective. So from this person's perspective, the apple falls right with him, and therefore the apple appears to be hovering, as it would if he let go of the apple while in outer space. The individual feels weightless, and the environment, if he looks in the local region around him, appears to behave as if there is no gravity at all. Now, why is it that this thought made Einstein so happy? Well, what it means is that by going into the right kind of motion, freely falling motion, you can cancel out the force of gravity. And that's vital because understanding gravity, Einstein realized, was a difficult, a profound puzzle. But now we had a way in. because merely by going into a certain kind of motion, he could cancel out the effect of gravity, thereby reducing the understanding of gravity to understanding that kind of motion. Einstein rightly felt that he could understand motion, and using that understanding, he believed he could leverage this idea into an understanding of the force of gravity. It would take him 8 years to do that, but by 1915, this thought led him to the new theory of gravity, which gave the world the general theory of relativity.
General relativity explained in under 3 minutes.
In 1907, just a couple of years after he does his theory of special relativity, Einstein's a little bit worried. Special relativity only applies to bodies in a constant state of motion. He's trying to figure out, how does that deal with acceleration? There's another problem that we had all inherited by then from Newton, which is that there's something called gravitational mass, how much something weighs in a gravitational field, and there's something called inertial mass, which is how much force does it take to push it and get it moving. And inertial mass and gravitational mass are the same, but they're two different ways of explaining them. And Einstein really hated when there was two theories explaining one phenomenon. He wanted to unify it. And so then he has what's called his happiest thought. He imagines a person just falling, free-falling in space. And he said, well, that person wouldn't feel gravity as he accelerated downward. And likewise, he imagined somebody in an enclosed elevator being accelerated upward in outer space where there's no gravitational field. He said, well, that person would still feel like there's gravity. He took something out of its pocket and dropped it, it would fall to the floor at an accelerated rate. There'd be pressure up on his feet, just as if he were standing in a stationary elevator car on the surface of the Earth. So he realizes what he calls the principle of equivalence, that the effects of gravity and the effects of acceleration are equivalent. So there must just be one explanation for gravity and acceleration. And that's what the general theory of relativity is. It takes the notion of constant velocity motion, which is special relativity, and says, how are we going to apply it to accelerate the motion? And he really comes up with this notion of a fabric of space and time, as if it's a fabric that sort of curves, like a trampoline fabric. You roll a bowling ball on it, and it curves because the bowling ball's there. Then if you put some billiard balls going afterwards, they kind of move towards the bowling ball. Why? Not because the bowling ball has a particular attraction, but because it's curved, the fabric on which they're rolling. Now imagine that in the 3 dimensions, but it's curving all 3 dimensions of space. Pretty hard, right? But also imagine it in 4 dimensions. Because what gravity does is the curving of the 3 dimensions of space plus time, the curving of space-time. Pretty difficult, but it all amounts to the most elegant theory in the history of science, the general theory of relativity.
So Albert Einstein suggests that gravity is a property of space-time itself, not a force. And it is a warping or a curving of the fabric of space-time due to matter. General relativity suggests that gravity is a property of space-time itself. It's a warping or a curving of space-time due to matter. If you have an object with a lot of matter, a planet, it warps space-time in such a way that objects that are traveling in a straight path will curve towards that object. Now, I need to show you how that works. This is what led Einstein to think about gravity as curvature. This is a lovely thought experiment.
Einstein's big breakthrough was the realization that he needed to describe gravity in terms of a kind of crazy-sounding idea, warps and curves in space and time. Now, how did he come up with this idea? Well, there's a little experiment, a kind of thought experiment that we can do together that will give you a glimpse into Einstein's thinking. And here's how it goes. Imagine that we have a box that is freely floating in outer space, no gravity at all. And imagine that you were inside the box, freely floating around, and you see there's a laser on that wall, and you push the laser, turning it on. What will happen? Well, you know the laser light will fire out and go in a perfectly straight line trajectory to the other side of the box.
Also, let's imagine, again, we have Superman eyes and can see the laser moving across the screen because we can see things moving that fast.
Good. Now, I just want to change this little thought experiment a little bit. And imagine that the box is actually hovering above the surface of the Earth. And we'll do the same experiment with the box freely falling toward the surface. The question is, what will you see inside of that box? And the answer, according to Einstein's happiest thought, is that your experience will be just like what you experience freely floating in outer space, because his happiest thought is that when you're freely falling, that cancels out the force of gravity from your perspective. So let's do that. The box is now in free fall motion. You turn on the laser, and from your perspective, the light goes straight across the box and hits at exactly the same point that it did when you were floating in outer space.
You okay with that thought? So how does curvature show up? Watch.
But now the key question is, how will this appear to somebody on the surface of the Earth watching the box fall? Well, from their perspective, the laser light starts over here and ends at this location on the other side, which means that the trajectory of the light is not straight.
See it? In one frame of reference, it traveled in a straight line, but another frame of reference, it traveled in a curve.
It's curved. And that's the first hint that curvature is associated with the force of gravity. Now look, it took Einstein a good 8 years of work to put mathematical might behind this idea and work out the general theory of relativity. But it all kind of starts here, with this first recognition of a link between gravity and curvature.
One of Einstein's students, a physicist named John Wheeler, famously said it this way. He said, "Space-time tells matter how to move, matter tells space-time how to curve." They affect each other. Under nerd trivia, John Wheeler also gave us the terms quantum foam and wormhole. He's one of the biggies in the physics world. So one way to visualize this is to imagine that space-time is like a flexible rubber sheet or a trampoline. So imagine a massive, stretchy sheet like this.
Relativity, the explanation for gravity is that matter bends space. And so you put mass in a place in space, it works space-time, and objects are not feeling the force of gravity, they're just following the natural curvature. And so this is a sheet of Lycra. Where do you get this? This is my old bike shorts. There's literally a spandex.com. You can get a sheet like this if you buy the sale stuff, so you don't care what it looks like, right? For like $20, maybe less, depending on the sale. And so you put matter, and it works space-time. And so if I have another object, it also works space-time. They feel that, and they're attracted to each other.
So you saw the two balls move towards each other, not because of a force, but because of curvature. You pause the video for a second because someone else showed up late.
That's Einstein's picture of gravity. Objects work space-time, feel that curvature, and move accordingly. And if you have more mass,
It's right there.
right there. more mass, it's going to bend space-time more. So if you have objects here, you're going to respond to that, right? So you put something there. Now it's attracted. Now in reality, that big mass would feel the space-time by the marble too, right? It would move a little bit, but we usually ignore that. Earth makes the sun move a little bit, but it's so small you can ignore it. The moon makes the Earth kind of wobble around a point 3/4 away from the center of the Earth. We usually don't account for that when we're looking at satellite motion. Well, instead of just letting go of one, what if I give it a sideways push? Now it orbits. Now it's losing energy, which wouldn't happen in the solar system, right? Not noticeably. There's some perturbations from other planets and things, but this one does lose energy and spirals in. If I don't push it as hard, it will do an ellipse. So one of the things I thought of to do is when you study the solar system, all the planets are going around the sun the same way. Why is that? Did God decide that he only liked clockwise? He's above or below the solar system, right? Why is everything going in the same direction?
So one thing we notice is all the planets go around the sun in the same direction. Why is that?
Answer is
they didn't originally.
It was different directions. But there was a preferred direction. This form had a slight preference one way versus another, and things go in the opposite.
There, do you see? All that's remaining is now going in the same direction.
And when it's all said and done, everything's going the same way.
So our early solar system, there was objects moving around the sun in either direction, all directions. They were smashing into each other, but as long as you had an imbalance somewhere, a lot of the collisions canceled out, but whatever was left ended up going in the same direction.
Usually that works 90% of the time. And so it won't work then. So I have slightly more in one hand than the other. Right? You want to get them so they spread out a little. When you do all that.
It's because they're colliding with each other.
One's going the wrong way.
There, you can see the 5 that are left are all going in the same direction.
Right? Now there also would have been, this is where this analogy breaks down. But those things are out of the plane also. Near the preferred plane also go. And so that's kind of cool. Now my students use a PHET simulation called My Solar System. So they've seen all this on the computer. And when we do this during our special relativity unit, they're like, hey, it's just like the computer. It's kind of cool that a spreadsheet of Lycra models things just like similar to the computer. Now, some things we discovered using this, since it's larger marbles, might as well set them out. But they bend space-time too, right? And so maybe you can get one thing to orbit another. There we go. So the Earth-Moon system, maybe? And so you can see that this seam, you can't buy Lycra this big. Rolls, and you have to sew it together. I've been told to use stretchy thread to sew it together. Next time I do it, I'll do that. And so just a little bit of thread fixes it. In the morning, when I first set this up, against the table, I'll be underneath fixing holes from last year. One time my principal walked, and I hear somebody in the room, and I'm underneath. And he's looking around for me, and he kind of knows somebody's around me. Oh, there you are. What are you doing there? And I go, what are you doing there? Ripping the fabric of space-time. What do you think I'm doing? Oh, you didn't see that. Another thing seen plastic ones. You've probably seen plastic Discovery Center, Discovery Center, children.
You sometimes see them in malls where you can put a coin in and the coin will slowly spiral down. And those are neat, but what you can't do with the plastic ones is have two masses.
San Jose has one, the Exploratorium has one, sometimes they have big shopping malls, sometimes they have big shopping malls. But one thing you can't do with those, is put two masses in. And so when we went to the moon,
here's the Earth and the Moon, for example.
When we first started, we sent our spaceships on what are called free return trajectories. So they would go to the moon, and they would come back, like a figure eight. And so that lets you show. And so that lets you show a lot smaller. But if you look at the plots of the free return trajectory back of the Apollo program, you'll see it has a figure eight sort of shape. You'll see it has a figure eight. So this takes a little bit of practice to be able to do the figure eight. These clamps around here. Tighter if it's not working. So Steve and I.
So there's our analogy for space-time. Now, I have a friend who's a general relativity specialist, and he hates that video and he hates that analogy because his argument is you're using gravity to explain gravity, because what makes the sheet sag? Gravity. So if that was better, I should be able to flip that sheet upside down and have stuff sag up as well, because that's what's really happening in outer space. It's causing a warping in 4 dimensions, not on a single flat dimension. So there are some problems with that analogy. I get it. Turn the page. You may have heard a few years ago, in 2015, the term gravitational waves. They were detected September 14th, 2015. We built something called LIGO, the Laser Interferometer Gravitational Observatory. There's 2 in the U.S., one in Spokane, Washington, one further east and south. I think it's in Louisiana. There's one more, I think, in Italy. And these are very, very, very sensitive devices. Like you imagine on a trampoline or on that rubber sheet, if you were to pound it with your fist, you would send ripples across that sheet. And so similarly in the fabric of space-time, if we have large massive objects colliding, 2 black holes, for example, it sends ripples out through the fabric of space-time. And we have detected them. So in 2017, the Nobel Prize for Physics went to Rainier Weiss, Barry Barish, and Kip Thorne for detecting gravitational waves. They were predicted by Einstein's equations. Einstein, in fact, wrote a paper on it, I think around 1920 or 21. Put your pencils down, look up. That's gravitational waves. One more video, and we're going to get technical a little bit. Yeah. Can you wait till when Worston gets back, please? Objects moving through space follow, we have a fancy name. We call it a geodesic. What's a geodesic? This is a path that seems curved to an outside observer, but appears as a straight line to the moving object following the path. Since, as far as the object is concerned, space isn't curved for them, it's curved for the observer. So now we're going to get a little bit technical. This is a really good explanation of how an object can appear curved and be straight at the same time. Put your pencils down, look up.
Einstein realized that there's another way for things to appear to fall together, regardless of their masses. Imagine a feather and a hammer floating in space. If the room is suddenly accelerated up at 9.8 meters per second squared, the feather and the hammer will hit the floor at the same time. Furthermore, whether it's the room coming up to meet them or gravity being suddenly switched on, neither object will feel any force pushing them. There's no way to tell which of these happened. This is Einstein's famous equivalence. He once admitted that his greatest thought ever was that of a man falling off of a roof. the man would
While
not
falling,
feel any
the man
forces
would
on him,
not feel
even
any
though he's
forces on
speeding
him.
up.
Even though
Free
he's speeding
fall
up.
is indistinguishable
Freefall
from floating
is
alone in
indistinguishable
space,
from floating
having
alone in
no
space,
forces on you,
from having
from
no
not being
forces on
moved.
you, from
What if
not being
gravity
moved?
isn't a
What
force
if
at all?
gravity
What if
isn't
things
a
fall
force
not
at
because
all?
they're being
What if
pushed
things
or
fall not
pulled,
because they're being
but because
pushed or pulled,
they're not
but because
being pushed
they're
or
not
pulled?
being
To
pushed
see how this
or
could be,
pulled?
we
To
need
see
to
how
talk
this could be,
about
we
straight
need to talk
lines.
about straight
What I have
lines.
here is a retractable
What I have
ID
here is a
badge
retractable
holder.
ID
This is a great
badge
way to
holder.
test for
This
straight
is a great
paths
way to test
because
for straight
the string is
paths.
always kept
Because
taut.
the string is
The
always
card I
kept
have
taut.
behind has
The
two
card
lines
I have
drawn
behind
on
has
it. And
two
if,
lines drawn
while I
on it.
pull the string
And
out,
if, while I
it
pull the
always
string
stays
out,
between those
it
two
always
lines. I will
stays
know
between those
that I
two
never
lines. I will
turned
know that I
while I
never
pulled it, because any
turned
turn will
while I
translate
pulled
into a
it,
different
because any
angle
turn will
between the
translate
lines
into a
on the
different
card and
angle
the string.
between the lines on the
Now,
card
if I
and
put
the
two of
string.
these on a
Now,
flat
if
table
I put two of
and
these
pull them
on a
out,
flat
always
table
ensuring
and pull
that
them
they
out,
go straight
always
ahead,
ensuring
they
that
will
they go
never
straight
meet.
ahead,
They will be
they
forever
will never
parallel.
meet. They will be
But now,
forever parallel.
let's put them on
But
a
now,
sphere.
let's put them
a curved
on a
surface.
sphere.
Again,
A
I
curved
pull
surface.
both strings
Again,
forward,
I pull
making
both
sure that they
strings forward,
always are
making
pulled out
sure that
straight.
they
No
always
turning.
are pulled out straight. No turning.
They came together.
Wait, they came together.
They didn't turn. Look.
They
Maybe
didn't
there's some
turn.
kind
Look.
of weird force
Maybe
that
there's some
pulled
kind
my
of
hands
weird
together.
force that pulled
And just
my
like
hands
gravity,
together.
I didn't feel
and
it,
just
but
like
it happened.
gravity, I didn't feel
No.
it, but it happened.
What happened
No.
was not the result
What
of a force.
happened
It was
was not
just
the
a
result
natural
of a force.
result
It was just
of
a natural
curvature.
result of
You might be
curvature.
thinking, wait a second.
You might be thinking,
are those really
wait
straight
a
lines?
second.
I mean, they
Are
don't
those
look
really
that straight
straight
to
lines?
me.
I mean, they don't look
Also,
that straight
what if
to
they
me.
just moved along
Also,
latitude
what if
lines?
they just moved
Then
along
they'd never
latitude
come
lines?
together, and
Then they'd
those
never
look
come
pretty darn
together,
straight.
and those look pretty darn
But they're
straight.
not. A straight
But they're
line
not.
never
A straight
turns.
line
And although
never
latitude
turns.
lines look straight
And
at
although
first glance,
latitude lines look
following
straight at first
one
glance,
requires
following
turning.
one requires
To find straight
turning.
line paths
To
on
find
surfaces,
straight
whether they're
line
flat
paths
like
on
this
surfaces,
or
whether they're
curved,
flat like
I
this
love
or
the
curved,
ribbon test.
I love the ribbon test.
The ribbon test is a very good way to tell if a line is straight or
Now you
curved.
can use an actual ribbon, but
Now you
I
can
have
use
found
an actual
that a
ribbon,
strip
but
of
I have
paper
found that a
works
strip
even
of
better.
paper
Let's take a look
works
at this path
even
right
better.
here.
Let's
It's
take a look at this
straight
path
at
right
first,
here.
but then it
It's straight at
curves.
first,
Now, if
but
two
then it
people are
curves.
traveling along
Now, if
this
two
curve
people are traveling
and they want to
along
stay
this curve,
together, the
and they
person on
want
the
to
inside
stay
will have to
together,
cover a
the
shorter
person on the
distance
inside
than the
will have to
person
cover
on
a
the
shorter
outside.
distance than the person
Since
on
both
the
sides of
outside.
this strip of paper
Since
cannot
both
change
sides
their
of this strip
lengths,
of
they'll
paper
help us
cannot
find a
change
straight
their
path.
lengths, they'll help us find a
If the
straight
strip of
path.
paper can lay
If the
flat,
strip of paper
we'll
can
know
lay
that we have
flat,
found a straight
we'll know
line. And as
that
you
we
can
have found
see,
a straight
the
line.
strip
And
can
as
lay
you can
flat
see,
and follow the
strip
straight
can
part
lay
of this
flat and
path.
follow the
But when it
straight
comes to
part
the
of this
curve,
path.
in order to
But when it
follow
comes
the
to the
path
curve,
now,
in order
the
to
strip,
follow the path
well,
now,
it has too much
the strip-
material on the
well, it
inside,
has
and that
too much
material
material
bunches up
on
and
the
leaves
inside, and that
the
material
plane.
bunches up and
Therefore, we
leaves
know
the plane.
that this part of the
Therefore,
path
we know
is not
that this part of
straight.
the path is not straight.
So this is the ribbon test or the paper strip test. If you lay it down, if you have to bunch it up to follow the path, you know it's a curve. If it can lay flat, you know it's a line.
Let's use the ribbon test to find straight
Let's use
lines
the ribbon
on the
test to
surface
find
of a
straight lines
cone.
on the surface
Well,
of a
from the
cone.
looks of it,
Well,
a line
from
directly
the
from
looks
the
of it,
base to the
a line
tip
directly from
seems
the
like it would
base
be
to
straight.
the
And sure
tip
enough,
seems
yeah,
like it
the
would be
ribbon lays
straight,
flat
and sure
on that
enough,
path.
yeah, the ribbon
But what
lays
about
flat on
a
that path.
ring
But what
around
about
the cone?
a ring around
Nope,
the cone?
doesn't work. Shorter
Nope,
distances
doesn't
around
work.
nearer the
Shorter
tip of the
distances
cone mean that there's
around
too much
nearer the
ribbon
tip of the cone mean
up
that
at the
there's
top,
too much ribbon
so it doesn't lay flat.
up at the top.
Let's
so it
see,
doesn't
what
lay
else
flat.
is there though
Let's
besides
see, what
this?
else is there
Well, if I
though
start
besides
here
this?
and just
Well, if I
allow
start
the
here
ribbon
and just allow the ribbon
to lay flat,
to lay flat,
I get a little curvy looking
I
shape
get a little
like this.
curvy looking
I say
shape like
curvy
this.
looking
I
because
say
while to
curvy
someone
looking
say at the
because
base, this
while to
path
someone
might
say
seem
at
to
the
go
base,
up,
this path might
slow
seem
down,
to go
change
up,
direction, and then
slow
fall down
down, change
faster and
direction,
faster,
and then fall
since
down
a
faster
ribbon
and faster.
on such a path
Since
is
a
flat,
ribbon on such a
it's
path
actually,
is flat,
for inhabitants
it's
on the cone's
actually, for
surface,
inhabitants on the
perfectly
cone's
straight.
surface, perfectly straight.
This is a geodesic. It appears curved to us as the outside observer, but I'm telling you, Riley, if you're following that line, walking along it,
If we trace the ribbon's path onto
If we
the
trace
cone,
the
we can
ribbon's
see this
path
clearly
onto
because
the
the cone can
we
be
can see
flattened.
this clearly because
A
the cone
straight
can be
line
flattened.
on a curved
A straight
surface
line
is
on
called
a curved
a
surface
geodesic.
is called a geodesic.
told you. I told you. It's a straight line.
Here is a geodesic on
Here
a sphere.
is a geodesic
The equator
on a
is
sphere.
Here's
the
another.
equator is one.
A line of
another.
latitude is not
A
a
line of
geodesic, it's not a
latitude
straight
is
line.
not a geodesic.
To see
it's
why,
not a
let's try
straight
to
line.
follow it with
To
the
see
ribbon.
why, let's try to follow it with
You know
the
what?
ribbon.
I have to keep
You know
kind
what?
of lifting it.
I have to keep
Yeah,
kind
see,
of lifting
distances
it.
around the sphere
Yeah,
become
see,
shorter
distances
as
around
we
the
go
sphere
up.
become
So there's
shorter
too much
as we
material
go
on the
up.
ribbon up
So
here,
there's
and
too much
it leaves the
material on the ribbon
surface.
up here, and
This
it
path
leaves the
contains
surface.
turns,
This
and in
path
order to
contains
turn,
turns,
a force
and in
has
order
to
to
act
turn,
on you.
a force
If no
has to
forces
act
did,
on you.
this
If
is
no
the path
forces
you would
did,
take.
this
Notice
is the
that the
path
ribbon
you would take.
begins
Notice
moving
that the
due
ribbon
east,
begins
but then
moving due
falls
east, but then
south.
falls south.
Falls.
Falls.
Einstein realized that curvature
Einstein
could cause
realized
things
that
to be
curvature
seemingly
could
attracted
cause
to one
things to be
another
seemingly
without needing
attracted
to
to one
invent
another
the existence
without
of
needing
forces
to
like
invent the
gravity.
existence of forces
But
like
attraction
gravity.
only
But
happens if
attraction
things move
only
along
happens
the
if things
surface.
move
If they
along
stay
the
still,
surface.
they
If they
well,
stay still,
they don't come together.
Well,
so for
they don't come
something
together.
at rest,
So for
how does
something
falling
at
begin?
rest,
I mean,
how
the
does
thing has to
falling
move in
begin?
this direction.
I mean, the thing has
but
to
it's
move in
at
this
rest,
direction. But
right?
it's at rest.
Well, yes,
right?
but it's only at
Well,
rest in
yes,
space.
but it's only at
and
rest
that's
in
not the whole
space.
story.
And that's not the whole
Down,
story.
forward,
Up,
backward,
down,
and left, right are
forward,
all you
backward,
need to
and left,
describe
right
where
are
an
all
event
you need to
occurs.
describe
But
where
a
an
complete
event
description
occurred.
will also need
But
to
a complete
describe
description will also
when.
need to describe
Together, these four
when.
dimensions form the
Together,
setting in
these
which
four
everything in
dimensions
our
form the
universe
setting in which
happens.
everything in our universe happens.
Space-time. Since we can talk about a falling pencil using
Since we
just
can
one
talk about a
spatial
falling pencil
dimension,
using
up
just
and
one
down,
spatial
we can use
dimension,
a piece
up
of
and
paper
down.
to
We can
model
use a piece of
space-time
paper
for it.
to model
Okay, so we've got
space-time
up and
for it.
down, but
Okay,
we
so
have
we've
to
got
add
up and
another
down,
direction
but we
the
have to
pencil
add
moves in.
another direction the
Time.
pencil moves in.
Now, if no forces
Time.
act on the pencil,
Now, if no
it
forces
won't
act
move
on the
through
pencil,
space.
it
It will
won't
only
move
get
through
older.
space.
And
It
as you
will
can
only
see,
get
if all
older.
it does is
And as
get
you can
older,
see,
it
if all it does is
won't
get
fall.
older,
If
it
space-time
won't
was
fall.
flat,
If
when I let go of
space-time
the
was
pencil,
flat, when I let
it
go of the
wouldn't go
pencil,
anywhere. But
it
now
wouldn't go
let's
anywhere.
allow the Earth, which is
But now
massive,
let's
to
allow the
manipulate
Earth, which is
space-time
massive,
into,
to manipulate
say,
space-time
a
into,
cone.
say,
Now,
a
with
cone.
no forces acting
Now,
on it, every
with
part
no
of the pencil
forces acting
follows
on it,
a straight
every part
line.
of the pencil
But on a
follows
cone,
a straight
as
line.
we saw
But
earlier,
on a cone,
such a
as we
path
saw
will
earlier,
look like this.
such a path
It
will look like this.
fall.
It
This
will
is because distances
fall.
around
This
the
is
cone
because
are
distances
shorter, higher
around
up.
the cone are
Time
shorter,
runs
higher
faster
up.
further from a
Time
massive
runs
object.
faster
But to
further
go
from a massive
straight,
object.
not
But to
turn,
go straight,
every part of the
not
pencil must
turn.
cover an
Every
equal
part of the
distance
pencil
in
must cover an
space-time,
equal distance
like
in
this.
space-time.
Only when
like
the pencil
this.
hits the Earth
Only
does
when
the
the pencil
repulsion of
hits
their
the
mutual
Earth
electrons
does the
provide a
repulsion of
force
their mutual
pushing the
electrons
pencil
provide
off
a force
the
pushing the
geodesic.
pencil off
For the
the
Earth,
geodesic.
time is a
For
series
the
of
Earth,
slices
time
from
is
this
a series
evolution.
of slices
The
from this
pencil's
evolution.
force-free geodesic
The pencil's
is why
force-free
it
geodesic
falls.
is
Not
why
a push
it
or
falls.
pull,
Not
just
a
the
push
pencil's
or
natural
pull,
tendency to
just the
follow a
pencil's
straight
natural
line
tendency
until
to follow a
something
straight line
acts on it.
until something
Now,
acts
we only
on it.
used one dimension of
Now,
space
we
and one
only
of
used
time
one
because
dimension of space and one
visualizing
of
our
time,
universe's
because
three of space
visualizing
and
our
one of time would
universe's
take us
three of
beyond the
space and
limits
one of
of
time
what
would
could be
take us
shown on
beyond the
paper
limits
or
of what could be shown on
screens.
paper
But
or
math
screens.
can take us
But
there.
math
General
can take us
relativity
there.
allows us to
General
calculate how much
relativity
mass
allows
and
us to
energy
calculate how much
curve
mass and
space-time,
energy
and
curve
has been used to
space-time,
explain
and
things
has
that
been used to
Newton's older
explain
theory of
things
falling
that
as the
Newton's
result
older
of
theory of
forces
falling, as
couldn't,
the result of
like anomalies in
forces
the orbit of
couldn't,
Mercury,
like
which
anomalies in
orbits
the orbit of
nearest
Mercury,
the sun and
which
is therefore
orbits
most
nearest
affected by
the
the
sun and
sun's
is therefore
grip
most
on
affected by the
space-time.
sun's grip
Many
on
other experiments
space-time.
have confirmed
Many
general
other
relativity's
experiments have
picture of the
confirmed
universe,
general relativity's
fitting the
picture of the
conclusion
universe,
that
fitting the
there
conclusion
is
that
no
there is
gravity.
no
There's just
gravity.
space-time.
There's just
It's curvature
space-time.
and us
It's
in it.
curvature.
As John Wheeler
and us
famously
in it.
put it,
As John Wheeler
space-time
famously put
grips
it,
mass, telling it how to
space-time
move.
grips mass,
Mass
telling it how to
grips
move.
space-time,
Mass
telling
grips
it how to
space-time,
curve.
telling it how
Relative
to
to
curve.
the Earth, we don't move
Relative
very
to the
fast.
Earth, we
Even
don't
jet
move very
airplanes move
Even
negligibly
jet
close to the
airplanes
speed
move
of light.
negligibly
So
close to the
relative
speed
to
of
Earth,
light.
we
So
move
relative
almost
to Earth,
exclusively
we move
through
almost
time.
exclusively
As such,
through
we
time.
are more
As
affected
such,
by the
we
way
are
time is
more
curved
affected
by
by the
mass
way time
than
is
how
curved
space
by
is
mass
curved.
than
This
how
has
space
led many
is
to
curved.
claim that for the
This
most
has
part,
led
you
many to
feel
claim
as
that
though
for
you're
the
being
most part,
pushed
you
into the
feel as though you're
ground,
being
not
pushed
because of a
into the
force
ground,
called gravity,
not because of
but
a
because
force called
time
gravity,
is moving
but
faster
because
for your
time
head
is moving
than
faster
for your
for
feet.
your head
Down
than for your
is
feet.
relative and
Down
always
is
changing,
relative
but it
and always
exists
changing,
because
but
of,
it
and is
exists
always in the
because of,
direction
and is
of
always
slower
in the
time.
direction of
Bertrand
slower
Russell
time.
called this the law
Bertrand
of
Russell called
cosmic
this
laziness.
the law of cosmic
Everything
laziness.
is naturally steered
Everything
towards
is
where
naturally
time
steered
is
towards
slowest.
where time
We call
is
this
slowest.
falling.
We call this
Going
falling.
down.
Going
So you don't
down.
have to keep anything on the down low. Time will take care of that for you. And as always, thanks for watching.
So you saw it's possible for something to be a straight line and curved. There was a few more things I wanted to talk about, but I'm going to hold off on these because I can sense some restlessness and some of you just want to stretch a little bit. So I'm going to pause here.